physics, you should have the notes paper for torque notes. Make sure you follow along and listen and learn. Don't just write on the paper. Make sure you're learning how to do torque problems. So far this year we talked about translational motion. That was our kinematic stuff where everything was going in straight lines. Even when we did projectiles, that was kind of translational because we treated them separately. We had the vertical part, and that was a straight line, and we had the horizontal part, and that was a straight line. So that was translational. Just in Chapter 7, we did circular motion. So to have anything going in a curved path or a complete circle, you know you need a net force toward the center. Now for torque, we're talking about rotational. So this would be something spinning, rolling. So our main differences between circular and rotation. In circular, something's going around an external axis. So that was like a planet going around the sun. Whereas rotational motion is where it's spinning on an axis within itself. So this would be like rolling or spinning. What causes a change in translational motion is a net force. What causes a circular motion was a centripetal force, which was also a net force. And now what causes rotation is a net torque. This is a Greek letter tau that we use to represent torque. And torque is a vector. It needs a magnitude and a direction. So if we're going to talk about the direction of something rolling or spinning, I can't say the left to the right. My directions are going to be clockwise or counterclockwise. So, what matters with torque? Like if I want to rotate the door on the hinges, it matters where I push. If I stand and push at the end of the door straight on, the door's not going to rotate. I need to push perpendicular to the door. My force needs to be perpendicular to the door if I want to cause the door to rotate. And that's all that matters. All that matters is where I push, how far I'm pushing from the pivot point, and at what angle I push. So torque is a force times the distance to the pivot point. So in the case of a door rotating, the pivot point is the hinges. And in order for there to be torque, the force and that distance from the pivot point must be perpendicular to each other. That'll make sense with some examples. So we're going to start with just general learning how to use the equations before we actually apply this to real life things. So for now, this is just a bar. This bar is 1, 2, 3, 4, 5, 6, 7 meters long. So that's just ridiculous. That's almost as long as our classroom. Crazy. We're just learning how to do the problems. And it's just real easy if I don't have to label measurements. Each one of these marks is a meter. Okay, so somehow we have this 7-meter long thing. And the thing itself in these examples has no mass. So a 7-meter long massless thing, crazy, has these 3 forces on it. A 10, a 10, and a 6. This is just my notation. You won't find this in a book. The star is where it pivots. So imagine like it's attached right here, and this bar can spin. This bar can either start spinning this way, or the bar can start spinning this way. And I'm going to find out by figuring out the net torque on it. So I'm going to find the torque from each one of these forces. I'm going to tell the torque from this one, the force is 10, and the distance from the pivot point, well here's the pivot point, is 1.5 meters. So my torque is 10 times 1.5, or my torque is 15 Newton meters. But now I need a direction. I would look at just this force and imagine it starting to rotate around this point. So if it's going to start rotating around the point, it's going to go this way. So that is the opposite of a way that a clock goes. So I would call that counterclockwise. You would not draw that. That is counterclockwise. Let's try the next one. Again, my force is 10, and this time my distance from the pivot point is 3 from the pivot point. Pivot point was here. 1, 2, 3. And if I have that one, if I make that one start rotating around the star, you can tell it's going to go this way. And that is the way a clock goes. 12 o'clock, 1, 2, 3 o'clock, 4 o'clock. Yeah, the clock goes like that, so that one was clockwise. Over here I've got 6 meters, and that is 4.5 meters from the pivot point. Here's my pivot point. 1, 2, 3, 4.5. Notice it's a distance. It's not a displacement. That is not a vector quantity. I would not have a positive 4 meters or a negative 4 meters. That's just a distance, not a displacement. So I multiply that, and I get that that has a 27 Newton meter torque. And that makes sense. Newtons for the force, meter for the distance. Newtons times meters. A Newton meter. And this one, you can tell, would also make it go that way, the way a clock does, so that is clockwise. Simple enough. Now I just want to figure out the net torque, the overall torque. Well, you can tell these two are working together. These are both clockwise. And that one's the opposite, counterclockwise. So it's just like if I would have had 2 norths and 1 south. I'd subtract. So I'm going to add these two together, because they're the same way, and I'm going to subtract that. And you can tell these are going to be bigger. So my net torque was 42 Newton meters clockwise, because my clockwise torques were bigger than my counterclockwise. So that was 30 plus 27 minus 15. That's how I got the 42. Maybe try this one yourself. Freeze the tape, and then just play it quick to check.
This is for the drivers. The ones who do more than defy rules.
So I hope we matched answers. Here is 20, it was a distance 7, so it was 140, and you can tell that one makes it go clockwise. The next one, 32 times 5, I get 160, and that is counterclockwise, goes this way. Next is 12, and it's 2.5 meters from the pivot point, so that's 30 Newton meters, and that's clockwise. Next one, it's 20, and it's 2 meters away. And that goes around the pivot point this way. You just make the arrow start going around the star. Counterclockwise, 40. And this one, 12 times 5, and also counterclockwise. When I combine those all together, I'm getting 90. So that was adding my clockwise, subtracting my counterclockwise, or the other way around. But I just have to have the ones that are working together. I can tell. Counterclockwise, counterclockwise, counterclockwise. These are working together. So the 160 plus another 100, so 260 counterclockwise. But here I only had 170 clockwise. So I took this minus the clockwise, and that's why I got the 90. Getting a little better here. You have to take a second to draw these yourself. Make sure you're putting them at the right position. This one 2 meters away from the pivot point. This one's 1 meter away from the pivot point. This one is 1, 2, 3 meters away. So make sure you draw those, label the angles and the forces. So remember, for torque, you only use the perpendicular part of the force. If you stand and push, this way or pull this way, that's not going to make this bar rotate. So that is not contributing to torque at all. It's just the perpendicular part of the force. So I would need to break that into components. But I only need this component. So that's the only one I draw. So I just need that blue force. I don't usually figure that out separate. I just throw that in my torque equation. So torque is force times distance to the pivot point. But I only want, if I look at my triangle here, I only want the opposite side of it. So I want the opposite side, and I know the hypotenuse. So I'd be using sine. So sine 40 times 20, that's that blue component. And then times 2, because that's the distance from the pivot point. I multiply that, and I get that it's 25.7. Just look at this blue one that we drew, and you can tell that goes clockwise. Next one. I just need this component. That's the part that causes torque. Again, you can tell if this is my angle, that would be the opposite side here. So I'm using sine again. Sine of 20 times the hypotenuse, 28. That's my force. 1 was my distance from the pivot point. Fire up the calculator, get 9.7 clockwise. Make the blue arrow start going around the star. clockwise. And the last one, again, it's my opposite side, sine of my angle times the hypotenuse. So this part giving my force, my distance from the pivot point was 3. Multiply, I'm getting 38.6 Newton meters, and that would be counterclockwise. If I make this start going around the star, it's going this way. I need to find my net torque. These two are working together. These two are making it rotate clockwise, so 25.7 plus 9.57. And this one's working against it, so I subtract the 38.6. So I have a net torque of 3.33 Newton meters counterclockwise.